All right, so here are the definitions of type 1 and type 2 regions. Type 1 region is sometimes called vertically simple. And this is the one that I think you should feel a little more comfortable than the other one. Vertically simple. Vertically simple means you have these functions, okay, which are sort of like functions of x. So you have g1, g2x, g1x. G1 is the lower one, and this region R. Okay, the reason this is called vertically simple is because vertically, okay, you have, this region is bounded by G1 and G2. Okay, so in this case, the way you set this is you have, of course, X ranges from A to B, right? And then for each X you pick, right, this is what I draw by blue. For each X I pick, G or the Y value goes from G1 to G2. So you are thinking of, you're solving for, these are solved for Y, and you can use G1x as the lower limit and G2x as the upper limit, and then you do f of x, y. And is this dy dx or dx dy? There's a very clear-cut answer here, right? It has to be dy dx because x is the one that goes with a and b, right? And then y goes with g1 and g2. So when the graph is shown this way, when the region is this way, we say it's a vertically simple region or type 1 region. Okay, type 2 region is the other one. Now, you don't really have to know which one is type 1 and type 2, but it makes sense to know these things so that whenever the book talks about type 1 or type 2, or when other people talk about type 1 or type 2, you know what that means. Okay, so in this case, you may have two functions like this. Now, these are functions where x is the dependent variable. X is, let's call this h1, y. Here, x is h2, y. All right, so now you can see clearly the difference, right? Because there, I can't talk about like the vertical line. I mean, if x is over here, x is, well, x crosses this, this h2 several times. And so I can't really define this as a vertically simple region. This is what we call a horizontally simple region. And what that means is you take the integral, and you notice here the y goes from c to d, right? And for each y you pick, x goes from this point to this point, where y is h1 y, and then the top is h2y. Now notice here, these will most likely have y as a part of the expression, but that's okay. Here you can have y, here you can't have any variables, right? And then the rest is of course the same, f of x, y, and then this is dx, dy, right? Again, the inside limits can have y in it, because when you're finished with this, you can have a y, you can't have x in it. And then once you do the entire integral, of course, you will not have x or y in the end. Okay, so and many times the region is both x and the type 1 and type 2 regions. Like in particular, this one we saw was definitely a type 1 and type 2 region. All right, I'm going to do a couple more examples, and then I'll let you get loose on your homework. And the homework could have some challenging problems because I want you to build your muscles. Here, I'm going to do two problems, all right, before I finish with this particular section. All right, I want you to integrate e to the negative y square over this region R, okay? And R is this region that I'm going to draw in an instant. There, okay? So the region R is a triangular region bounded by 0, 0, 2, 2, and 0, 2, okay? So how do you set this up? Okay, so this is, that's not bad, right? Let's think of this as a type 1 region, because this actually is both, right? Type 1 region means that I do ask this question, what does x range from and to? x goes from 0 to 2. That is the biggest part of x, right? So x goes from this point all the way to this. That's what covers the entire region R. And then for each x, we do this kind of thing, right? So what happens here is x goes from, and this line, by the way, is y is equal to x, right? Because it goes from 0, 0 to 2, 2. So y goes from x to 2. That looks pretty simple, right? And then you do e to the negative y square dy dx. All right, and at this point, I'll say good luck trying to find the function whose derivative is e to the negative y square. Okay, and you think hard and hard, and you spend a couple of months trying to figure this out, and maybe a couple of years and a couple of lifetimes. You will not be able to find any function whose derivative is e to the negative y squared. Okay, in fact, unfortunately, or fortunately, somebody proved that you cannot have any simple elementary function whose integral or whose derivative is e to the negative y squared. All right, so you can't do it this way. So then what? Remember the very first example I gave you in part 1 of this? Sometimes it pays to switch the order, okay? So type 1, can't do it. Type 2, sometimes you may be able to do that, right? So the type 2 is going to be very different, right? How different? Well, then you ask the question, y ranges from what to what? And here, the lowest point y is 0. The highest point of y is 2, okay? And then watch carefully, for each y you pick, you go from this point to wherever it touches that, right? So that means y goes from 0 to until you hit this line, y is equal to x. But you don't say y is equal to x anymore. The question is x goes from 0 to what, right? So x goes from 0 to wherever you hit this line, which is now x is equal to y. I know it's the same thing as y is equal to x, right? But you have to write y here because the question is for each y, what does x go from and to? The answer, x goes from 0 to whatever that y is, all right? And so that, now this is what you get. And you may think, what's the difference? I mean, that's pretty much the same thing, right? Well, it turns out, well, can you do this, right? Can you? I don't know. You may be able to. Well, take a look. This, with respect to y, is a constant. Did you notice that? E to negative y squared can be considered a constant. And so this is just like 5. What do you get when you do this? That's 5x plus c, right? So then you have x, and then it goes from 0 to y. You plug in y and 0 for this x, and lo and behold, you have y minus x here. And so this becomes negative, well, the integral of, here, let me go ahead and write this in the next line because I know what the next to the next line is. All right, so this actually becomes, what does it become? From 0 to 2. And then you have e to the negative y squared, and then y dy. Now, what's a big deal here? Okay, well, it's a big deal because now you can do u substitution. See, I couldn't do u substitution here, but thanks to this y, let's let u be negative y squared, okay? And then du is going to be negative 2y dy, all right? Now, the y is supposed to go from 0 to 2. So let's go ahead and write this. Y is supposed to go from 0 to 2, right? So now you say u goes from 0 to what? Actually, maybe I should not do u is equal to negative y squared. Let's just go from, let's let u be y squared. Okay, I think that makes it a little better sense. That's okay. This is fine. All right, so the point is, as u goes from 0 to, as y goes from 0 to 2, u goes from 0 to negative 4. Okay, let's keep that in mind. And so now we get to do this, right? So this becomes now, it's not from 0 to negative 2, but 0 to negative 4. And in fact, we have a constant coming in. What is the constant? I have to have -1/2 outside so that this can be written as e to the negative or e to the u, right? Because u is this. And then you have y dy, but because I divided the outside by -2, I can multiply the inside by -2. This becomes -2 y dy, which is exactly this. Okay, I hope you know how this conversion works when you do u substitution. You know, so you divide. So see, the thing is, you want, okay, all I have here, this is the Disney explanation. Okay, all I have is y dy. I wish I had -2 y dy. So when you wish for something to be there, when you wish upon the stars, sometimes you get to see that, right? What do I mean by this? Well, look, you look really carefully here, and I start to see -2. That's what I want. Great. Well, I can't really do that, even if nobody's watching. Okay, I can't get away with this. So that's why I compensate for that -2 by dividing the outside by -2. So this is what happens. -1/2 times the integral of, and I change the numbers here, and then this becomes e to the u, and then -2y dy is what we call du. The rest is very simple, right? So this is e to the u, and then this goes from 0 to -4. And so that's -1/2 e to the -4th minus e to the 0. And so that is -1/2 1 over e to the 4th minus 1. Now, you can leave it, or you can just, because it's negative outside, you can change it to 1/2 1 minus e to the 1 over e to the -4th. You can also write this as 1/2 minus 1 over 2 e to the 4th. Doesn't matter how you write it, but that's the answer to this question. All right. So hopefully this has made sense, and this is the right answer here. Okay, so my final example is this. Let's say your region looks like this. It is bounded by this thing. What is that? Okay, that looks like y is equal to x squared. My region here is the inside of this parabolic area where x and y are both positive, and R is bounded by the horizontal line y is equal to 4 and the y-axis and y is equal to x squared. Sometimes it's written, described in exactly that way, okay? And say, so let's say find the integral of f of xy, which is 6xy squared over the region R. All right, now I'm not going to tell you. Actually, I can say set up, you know, and then you should be able to set this up either as a type 1 or type 2 region, right? So, and sometimes the order may be specified. Sometimes it may say, do this in the dy dx, okay? Sometimes the problem may say, do in the order of dx dy. Okay, but either way, you should be able to do this, right? So guess what? If it's dy dx, what do you say first? X goes from 0 to 2, okay? So in this case, if you think of the right and left bounds, you know, well, x goes from 0 to 2. And for each x between 0 and 2, let's say you pick this point here, y goes from what to what, right? Well, y goes from not 0, it always ends with 4, right? No matter what x is, it always ends with 4. And the beginning point is on this curve, which is x squared. So you can set this up in this way. It's going from 0 to 2, and then x squared to 4. Remember, you are going to spend a lot of time doing these. And then the rest of the part is not hard, okay? So this is how you set this up if you are trying to do this integral in the order dy dx. All right, and I will just do this partially. What happens in the middle, in the first is because you're trying to integrate with respect to y, this becomes 2xy cubed. See that? This part becomes 2xy cubed, making sure that when you differentiate this with respect to y, you get 6xy squared, which you do. right? And then you evaluate these at x squared and 4. Those are the y values. All right, so then this becomes from 0 to 2 of 2x, and then 4 cubed, 64, minus x squared cubed. That's x to the 6th power dx. All right, and then the rest is, okay, I am going to just maybe do this partially. This is, this becomes, let's take the 2 out here, okay? This is a 64x minus x to the 7th, all right, dx. I will let you do the rest of this. I think you can easily do this integral because this is a calculus 1 integral. Verify that you get 192. You may want to pause this video at this point. Just make sure you can do this integral and say you get 192. All right. Type 2, I want you to be able to do this in the other order as well. Okay, dx, dy. In this order, what are you asking? Okay, so you're asking, here's your integral, and this is 2, this is 4, this is your region R. If you are asked to integrate in this order, dx, dy, the first thing you ask is, what are the y values? Y goes from what to what? The answer, 0 to 4, right? And then for each y, so now you have to go this way. For each y, x goes from 0 to what? Y, x goes from 0 to what, right? And the answer is x always ends in this equation on this the parabola. But you have to solve this for x. What is x in this case? It's the square root of y, positive square root of y, because it's on the right-hand side of the equation, of the y-axis. So x goes from 0 to the square root of y. And so that means your integral then will be from 0 to 4, 0 to square root of y, and then you have 6xy squared. And what's the difference? This time you do dx, dy, right? Then the rest of this, I guess, goes smoothly. Now, if you integrate this with respect to x, you get 3x squared, right? Y squared is considered a constant. And then this is what you'll end up with, right? And then, again, I am not going to carry this to the end, but let's see, I always like to take my constant outside, so this becomes x squared. And remember, well, no, that doesn't become x squared, right? Because now then we have to plug in these guys to x squared. So the first one becomes, and maybe I should be a little more specific in trying to write this. This is the square root of y squared, y squared, minus 0 squared, y squared. Of course, that's what you have. Okay, hopefully you can see what's going on here. This is 3 times the integral from 0 to 4 of, what's this? That's y cubed dy, right? And that, I am losing my screen here. All right, so this becomes 3 times 1 over 4 y to the 4th, 0 to 4. This is 3/4 times 4. Okay, you can cancel. So this is 64 times 3. And if you do this, you, of course, get 192, which is what we got initially. All right, so learn how to do integration in both directions, or both, dx, dy, and dy, dx. All right, so that's it, 5.2. Now we know how to, or you know how to integrate double integrals over regions that are not necessarily rectangular. All right, and so practice, and it would take some time to get used to, switching the order and writing the function in terms of x as opposed to y and so on. But I think with your hard work, with your diligence, you can fairly quickly learn how to do this and feel comfortable. All right, so be ready to switch the order dy dx into dx dy and vice versa, because the next time I see you, we will be doing some polar integration. That's right, double integrals using polar coordinates. All right, so look forward to that. And until then, I hope you have a great week. Take care. All right. Bye.